but I haven't looked at it.
Okay. So has anyone looked at it already?
No.
Okay.
No.
Just wondering, yeah, how many footings are there to be designed? Can someone open it now? And please check for quick.
Looks like one.
Okay, so it's gonna be only one footing that you guys will be designing. I want to be sure of this. And which footing is this? Is it the smallest, the largest, something in the middle?
In the middle?
So it is not the largest column load?
The largest column load and largest foot.
Largest column load, okay. So where do you get this column load from? The dead load and live load? Was it given the problem?
The submittal before it.
Okay, so from the previous submittal, you have the column load as dead load and live load. And then you have been asked here to do two major tasks. One of them is to size the footing, which means soil design, soil analysis. You're gonna have your dead load and live load, you figure out the service load and based on the allowable bearing pressure. Where'd you get the allowable bearing pressure from? Just want to be sure that you guys know your way to do the problem. How much is the soil bearing pressure? Was it given in the statement, project statement, or was it given in this specific problem, submittal?
It's in the statement. It's 3,000 psi.
3,000, very good, all right. And I guess you guys, you have enough slides and enough examples to be able to design, to do complete design for one footing. This will include sizing the footing, and then after that, the reinforcing at the bottom of the footing. And is the footing is going to be rectangular in shape or a square in shape? Does it say somewhere it's going to be square or rectangle, or what does it say?
Square footing.
Square. Okay, good. All right. And then after you find out the reinforcing, you're going to do one-way shear check and then punching shear check. Now, for this footing here, when you have the column right in the middle of the footing, is this considered to be interior column situation, or is it going to be edge or corner when you do the punching check?
Interior.
Interior. Thank you very much. So if any of you is missing any of this information, everything here is recorded and you can watch the game whenever you have a chance. I'm trying here to cover the typical questions that I usually hear from students about this foundation design. Interior case, where do you get the column load from? Where's the bearing pressure and this kind of things? How about the concrete strength? Where did you take it from? Is it also in the statement? Can someone please check and see in the statement if there's foundation concrete strength? Is it there or no?
Yeah, it's there.
Okay, excellent, very good. All right, good. All right. So what we are moving forward here to work on is going to be something that we call development length and splice length. Here's one beam and a couple of columns that we're trying here to do a design for. This beam, in your design, you may assume it's going to be simply supported, meaning that at each end here, you're going to have a pin, like roller, a pin on a roller, you know, it's going to be like hinge support. Meaning that no moment is going to be developed here at this end and no moment is going to be developed here. And the maximum moment is going to be only in the middle. But when you put the reinforcing together and you put the beam, the concrete beam, whether you want it or not, this end here is going to develop some moment. So it is not really a hinge. So in your analysis, you assume that here you have a hinge, but in reality, you don't have an actual hinge. Because let me look here at this from a close look here and see what happened. Look to the reinforcing. The top reinforcing usually is going to be provided with a hook at the end. This cracks in the middle of the beam, we're going to call this to be flexure cracks. This is going to be due to moment. This cracks on the top of the beam right here at the end. It's going to be also flexure cracks. This cracks, the diagonal cracks that goes at 45 degrees, this is going to be shear cracks. And of course, we have here symmetry. So during my design, I'm assuming that I have here positive moment, tension at the bottom only, but in reality, I'm going to have also negative moment. And because of this partial fixity, if you like to call it this way, partial fixity, it's not 100% fixed. You see here that the column is going to start also to rotate. See what happens to the column? It's going to start to develop this shape. And some tension is going to develop here on this side. And also some tension is going to develop here inside of the column. How about here, the bottom reinforcing? Someone's going to say, in the bottom reinforcing, I have the series continuous. In the middle, I'm going to have here tension. So I can come here and mark this and say, in here, I have some tension force. So right here is going to be tension. How about here in the top? The top is going to be compression. At this end, I'm going to have some tension at the top. And also I'm going to have some compression at the bottom. And here's the rebar. You see this dark red line, and here's going to be kind of faded because of concrete. Therefore, this area here of the rebar is exposed to compression. Now look what happened here at the end. This bar here, the tension and compression is going to have some values, right? Meaning that this bar here is going to be exposed to compression in this direction. It is pushed this way. Same thing from this side. This bar exposed this way. When you look here at the top reinforcing, you're going to see here that you're going to have some tension in the top rebar. And if you have this tension, you cannot just sub the bar right here. Because if you sub the bar right here, you're going to be just pulling it out of the concrete. This is what you call here slippage. You don't want this to happen. So you'd like to come here at the end and provide this hook. This hook is going to stop the bar from being pulled out. So whenever that you have a rebar, you cannot just stop it here. You need to hook it or extend it. Now, where is the section of critical moment, the maximum moment that I need to design for? Can I say it's going to be right in the middle of the column, or should I say at the face of the column? Which of the two? Face of the column or middle of the column? The one that I really need to design my moment for. Anyone there? Any idea? Okay, from Jacob, he says it's going to be at the face of the column. This is correct. At the face of the column, this is why I have here the maximum moment. Because once you get through the column, the depth of this structure is going to be the entire column height. So it doesn't count. So I'm going to say this is going to be the support itself. I'm going to take it at face of support. So after the face of support, where you have some tension force, you cannot just sub the rebar. You need to extend the rebar this length and then hook it. Why do you hook it? Because the hook is going to give you more strength. The straight embedment, as we call it, embedment length, is going to be weaker in transferring the stresses, the stresses between the concrete and the rebars. So providing a hook is going to help out. Okay. Let me see here this reinforcing details. So if you look here at this rebar, which is exposed to some tension force, we're going to hook it at the end. The hook length is going to be measured from the face of the column to the end of the hook, meaning this distance. If I may put it here in red, I'm going to say this distance here is going to be the hook length or embedment length of the hook. So right here at this point, this rebar is going to be exposed to tension. Start from this point all the way to the end of the hook. You are trying to take the tension force from the rebar and transfer it to the column, to the concrete itself. So we call this development length. And this is the reason that we have this name. As you see here, they call this development length. Development length. Development length means, again, that you're going to have some tension force on some rebars, and you'd like to transfer it completely to the concrete surrounding this rebar. How do you do this? You are using here the bond mechanism between the rebar and between the concrete beam around it and column. A little bit more details. Also, usually the bottom rebars, in many cases, would like to hook it. So look here at this bottom rebar. It goes like this and then it goes up. Top rebars also is going to be hooked. So if you go here to the previous slide, in some cases, we keep the bottom rebars straight because at this point here, the force is going to be much less. In other cases, we would like to hook the top and bottom rebars. Again, the length of the hook is going to be measured from this point all the way to the end of the hook. This hook length here, you're going to say, well, it's going to be just based on the column. It's going to be based on the column size, because if you go here to the previous slide, you're going to say, okay, you don't really have control on this because it's going to be controlled by the column size. I'm going to say, yeah, this is true. This is the way it looks. But you need to do your analysis and be sure that this distance needed is going to be within the column length. So what's the column length? You see the distance from here to there. So what you need to do, determine the needed length to transfer the force from the rebar to the concrete and compare to this column length. If this hook development length is going to be within the column length, you're good. You can just take the rebar to the end of the column. The problem if you need more length than the column size. So in this case, you need to put here a block. You need to extend your beam and put a kind of a block here at the end, which is going to be, it's not going to be the nice thing that you'd like to see in reinforced concrete structure, but in some cases they do it. Just have an idea here how the rebar size is going to be, and this development, the 9-degree development length for a hook. We call this 9-degree hook. 9-degree hook, it means you have a straight rebar, and then at the end you're going to have this 9-degree hook. Also, we call it standard hook. With a standard hook, it comes with certain dimensions and certain size relative to the rebar size itself. Look how it can be big, right? For number 18 rebar, a person can be just standing here. So it can be really large when it comes to this standard hook length. Also, when you have, this is going to be like a beam. This is going to be a piece of the beam, right? This is right at the column. So what you have here, you have a beam to the right and then a beam to the left. And here's the column location. In this section AA, look how many bars you have. You have 5 rebars, right? 1 and then 2, 3, 4, 5. When you cut this section here. So all the rebars going to be happening at one level. But when you look at this elevation here, they call this to be Y bars. And then the top one's going to be X bars. But in here, when you look at the Y bars going to be this rebar and this rebar. So I may just point at it. So I'm going to say this is going to be the Y bar, and this also is going to be the Y bar. Now, where's the X rebar? X bars here is going to be the 3 rebars, 1, 2, and 3. In plan view, here are the X rebars, 1, 2, and 3. And the Y rebars is going to be this one, and then 2, and then this stop at certain point. So when you look here at the section, you see that all of them, they happen at the same level. When you look at the plan, it doesn't really show that they happen at the same level or not. But when you look at here at this elevation, they show that they happen in 2 levels. So which one is correct? You're gonna say this give you the correct one. This give you the correct, this give you the truth. This is the way it is built. The reason that we showed it here in 2 lines is because when you do here your elevation, if I'm gonna stop the rebar right here, I cannot show it to you visually. I cannot explain that at this LD, which is development length, I'm going to be stopping this rebar. It's going to be more confusing. Why? Because you're going to see the two lines and they cover each other. So it doesn't make sense. So just for illustration and to show what's happening, I'm going to show it here in two levels. And look at this statement here, this sentence, it says single layer, which means they don't, there is no really any space between them. They happen the same level. Now, right at this section A, you see this section A, and here's section B. At section A, I need only 3 rebars. So right before this to the left, I need 5 rebars. So in this location, in here, I may need here 5 bars. Oops. So here, I need 5 bars. At this location, I need only 3 bars. So 2 of this 5 rebars that you're looking at, you see here, I have here 5. I need to stop 2 of the 3 bars right here at this section A because I don't need these 2 rebars anymore. But I cannot stop them right away. I need to develop them first in the concrete. So even in some cases that you don't need this rebar at this location, but you're going to be extending them for this L sub D, which is development length. And in this case, we call this straight development length. So we have here 2 cases. One case when I have a hook, and the other case when I have a straight development length. Now for the same rebar size, my question to you guys, which one do you think is going to be shorter? Is it the straight development length or the hook to develop the bar? Develop the bar means to transfer the force within this rebar to the concrete. I'd like to hear your comments.
The hook will be shorter
Why is that?
because the straight rebar relies only on friction and the connection to the concrete, whereas the hook pulls on the actual concrete.
Okay, and in the hook you have some bearing, right? So in the hook you're gonna have some end bearing when this hook here is pushing against the concrete, and also you have the friction along this length. Good answer, Angel. Thank you. All right. So this L sub D for the straight development. Look at this. This is gonna be for the straight development length. We have an equation for this L sub D. This L sub D, it has an equation. The equation says L sub D equals, then it looks like complicated, isn't it? You have too many terms, weird stuff. So we need to figure out what's going on. This L sub D is going to be equal to a constant, and this constant is going to be 3 divided by 40, just numerical number. F sub y is the yield strength, and if you like to use it in this equation, it has to be in psi. You remember this? Any equation that has strength, it needs to be psi unless you are very careful. For example, if you have psi divided by psi, it's going to be the same as ksi divided by ksi because you can cancel each other out. But in this case, it has to be 60,000. If you use 60, grade 60, right? F prime C is a concrete strength. We're aware of it, which also is going to be psi. This lambda factor is going to be this factor for lightweight concrete. If you guys recall the lightweight concrete factor, if you have lightweight concrete, you use lambda of 0.75. If you have normal weight concrete, it's going to be 1.0. So I guess I was able to cover this easily. I have this information from the past, right? I know these variables. I hear about them. That was easy. I'm going to skip this box and just jump here to the end. What is dB? Anyone knows dB? What is dB?
Depth of bar.
Bar diameter? Which bar diameter? Oh, the bar that you want to develop, not any other bars, right? If you are developing number 6, it's going to be dB, it's going to be 3/4 of an inch. If you develop, let's say, number 9, it's going to be 1 1/8. Number 8 is going to be an inch, right? It's going to be for the rebar that you develop. Now I'm looking here at the three factors, and this factor is called psi. This psi sub t sub e sub s. You just multiply by each other. So we need to know what are these factors for. The first one is a factor to differentiate between top reinforcing and bottom reinforcing and vertical reinforcing. So if you have top reinforcing, we're going to have a special treatment. If you have bottom and vertical, we're going to have a separate treatment, separate values. If psi sub e is going to be for epoxy coated. Did you guys hear before about epoxy coated rebars? Just for curiosity here.
Yeah.
What is this used for, Mike?
Slow or inhibit corrosion.
Exactly. So, yeah. So when you have like corrosive environment, one of the options that you can do is to use epoxy coated rebars, because the epoxy is going to be delaying the corrosion, right?
Yeah, but I've also been told that it makes them, for lack of the right term, more slippery.
Exactly. This is why when it comes to the bond, absolutely, this is a very good point. So when it comes here to the bond, because this length is based on what? Based on the bond between the concrete and the rebar. So when you have epoxy coating, it means this factor you should expect it to be higher than the one without any epoxy coating, which means that you need more length. So when you have epoxy coated rebar, right, the bond is going to be less. When the bond is less, this factor is going to be higher. And the final development length needed is going to be higher. Make sense? Okay, we're going to see the factors. If size of S, it depends on the size of the rebar. So for each rebar, you're going to have different size of S. Just think also about the bond. The bond is based on the surface area of the rebar. So when you take, for example, AS divided by, let's say, by the perimeter, or the other way around, the perimeter of any circle divided by the cross-section area, you're going to see that the ratio is not going to be usually constant, because it's going to be based on the diameter. So for example, if you have smaller rebars, you're going to have more surface area, correct? The surface area for a smaller rebar is going to be larger than that of the larger rebar area. For example, if I have here two rebars number 5, anyone knows the cross-section area for number 5? Can you help, please? Rebar number 5, cross-section area equals 0.31. Thank you, Jorge. Thank you. So 0.31 is going to be the cross-section area for one rebar number 5. How about number 7?
Point 6.
0.6, almost double, right? Isn't it? Thank you, Zuli. Thank you. So it's going to be 0.6 square inches, meaning that each one of this number 7 rebars is going to be equivalent to cross-section area to 2 number 5 rebars. Am I correct? Roughly 0.6 versus 0.62, they're almost the same. But how about the surface area? Which one do you think is larger? 2 number 5 would get you larger surface area, or 1 number 7?
Two bars.
2 bars. This is, I mean, this makes sense now that the bond between the number 5 and the concrete is going to be larger than that for the number 7 if you have the same cross-sectional area. This is why we have the psi sub S. So now I guess I understand the reason that we have the 3 factors. So one factor for being top or bottom rebars or vertical rebars. The second one is going to be for the epoxy coating. The third one is going to be for the size. And then I have also here more factors. dB, I guess I know dB is the same dB. It's going to be just the same. I have 2 factors here. One's called KTR and the other one's going to be called CB that I need to understand. Basically, I have 5 factors that I need to know. 5 new factors. I know f sub y, I know f prime c, I know the lambda, I know db. So I'm gonna have psi, cb, and ktr. So let's take them here one by one and see the effect and how we can handle it. Here is the CB. I need to understand what is this CB. C is like the clear distance, but clear distance to where? To the center of the rebar. So it's called the CB that you're going to be using here for this rebar, right? In this equation is going to be the smallest center of bar to edge distance. Meaning, for the same rebar, you may have 2 edge distances. Like, for example, this rebar here. So in here, for the same rebar, right, you can have 1 edge distance, another edge distance. I understand that. So for this rebar, for example, which one is going to be the smallest edge distance from the center of the rebar to the edge of the concrete? Is going to be this distance here, the vertical or horizontal one?
Professor, the screen stop sharing.
Oh. Tap it. Do you see it now?
Yes, thank you.
Okay, thank you. So for this rebar here, I have 2 edge distances. I have the vertical and horizontal distance. Now, which one do you think is going to be smaller based on this information available to you? You're going to say, this is 2-inch clear typical. What does it mean by typical? Typical means in all sides, you're going to have the same 2 inches. So for this rebar here, I'm going to say the distance that I'm talking about, which is CB1, right? This CB1 is going to be for this rebar. It's going to be the same as this distance from here to there. It's going to be also CB1. You see this distance from here to there? Why? Because the cover is going to be the same. It's going to be 2 inches plus ½ inch for the tie size. Number 4 means ½ inch. And then this rebar here, let's say if this rebar is 1 inch, because number 8 is going to be additional ½ inch. So from here to there is going to be 3 inches. So for this rebar here, CB, in the vertical, horizontal is going to be the same, it's going to be 3 inches. Someone's going to say, how about one of the 3 bars in the middle? What's going to happen to it? I'm going to say this rebar in the middle, I don't have a close edge to it. So in this case, what the code says, the top one is easy, you can figure it out. But the other one to this direction here, you just draw here a vertical line like this dashed line to be right in the middle between the 2 rebars, right? And then you come here, you say that the distance from the center of this rebar to the dashed line is going to be the other edge distance. So for example, for this rebar here, I'm going to have CB1 and CB2. Here's CB1, which is at 3 inches. Now the distance, clear distance from the 2 rebars is called to be 3 inches, clear typical, right? 1/2 of it is going to be 1½ inch from here to there. And then another ½ inch for the rebar radius. So I'm going to say at the end, I'm going to have here 2 inches. So someone can say, okay, let me find out the total distance from center of the rebar to center of the rebar. Center to center is how much? It's going to be 3 plus 1 inch. Divide by 2, it's going to be 2 inches. So in a case like this, the CB that you need to use in this equation, which is this one here, is going to be the smallest of these 2. And in this case, I'm going to be using the 2 inches. See, it says here, based on bar spacing, this is what controls, therefore use 2 inches. Are we good about this CB or not? Any questions?
Can you explain CB2 one more time, please?
Okay. Again, CB is a clear distance from the center of the rebar to the concrete edge or face. All right. This is what the code says. This is what we're going to be using, this CB in the equation. So someone's going to come here and say, in cases like this, you can have here 2 edge distances. Because the rebar here, it has 2 faces. It is not just going to be 1 face. So what the code says, use the smallest. Because when you use the smallest here, you're going to have less concrete to provide confinement. And therefore, this CB would like to use the smallest, right? You know, when the rebar is confined in lots of concrete, the bond strength is going to be high. But when the amount of rebar and the amount of this clear cover is going to be small, the bond is going to be small, and therefore development length needed is going to be larger. Look, where's the CB location at in this equation? When you increase CB, what's going to happen? You reduce this L sub D. So to be conservative, you take the smallest CB possible that you have for this specific rebar. So this gets smaller, L sub D is going to get larger, which means that you're going to be a little bit more conservative. So for this rebar here, the CB is going to be 2 of these 2 distances. This is one of them, and here's the other one. For this specific rebar, you have 1 edge distance here, 1 edge distance here. Again, from the edge or the face of the concrete to the rebar of concern. So in this case here, to figure out the CB1 is going to be equal to 2 inches plus the tie diameter plus 1/2 of this rebar diameter, which is 3 inches. So this works fine. I mean, it is easy to explain it when it comes to a corner rebar here. But the question is, how about this rebar? Where's the edge distance? I'm going to say I have here 2 edge distances. This one is a clear one that you can just look at and figure it out yourself. The other one is going to be based on having imaginary surface or edge of the concrete, free surface, which happens right between these 2 rebars. So again, what you need to do, you draw this dashed line between the 2 rebars, and then figure out the distance from this dashed line to the center of this rebar, which is CB2. At the end of the day, use the smaller of the 2 values. We're good? Repeat.
Yes, thank you.
Right. Now, we figure out here one factor, C sub B. How about this size? Let's go through them. If psi sub T here, it says for the top rebars. It says when you have here top rebars, we need more development length. And the factor of psi sub T is going to be 1.3. This happens when you have more than 12 inches of concrete below the rebar. So someone's going to say, how about if the entire depth of the slab is going to be 8 inches? How about the top rebar of the slab? Would you call it top rebars according to this equation? Let me think. The entire slab is going to be 8 inches, and the top cover is going to be at least 1 inch, meaning you're going to have the depth below the rebar. It could be maybe 6.5 inches or 6 inches. This is not more than 12 inches. It means this top rebar in the 8-inch thick slab would consider to be bottom rebar. I don't really need to include the 1.3 factor for it. How about vertical rebars? What size of T should I use? I need help. Vertical rebars, is it mentioned here? You see here anything about vertical? I see it. It says going to be 1. Why? Because it's going to be other reinforcement, including vertical and bottom reinforcement. All right, now let's talk about this size of T, sub E for the epoxy. When you have epoxy coating, is going to be 1.5. But this 1.5 is going to happen when you have the cover is going to be smaller than 3 times the bar diameter, which means when you have this bad condition of a smaller spacing or smaller amount of concrete surrounding the rebar. You see, when the clear spacing is going to be less than 6 times the bar diameter, which means the rebar are closer to each other, or when the concrete cover on the top or to the side, any concrete cover is going to be smaller than 3 times the bar diameter. So you know that you don't have enough concrete to surround the rebar. In a case like this, and you have epochs in the same time, your psi sub e is going to be 1.5. If the rebars are spaced in a good way, like you have enough spacing, more than 6 dB, and you have enough concrete cover, your psi sub e is going to be 1.2. If there is no epoxy coating, it's going to be 1. So I said, okay, just a bunch of factors. And what I need to do is to see the case I have and find out these factors. So this factor shouldn't scare me. And they tell you here that when you, after you are done with these two factors, multiply by each other, say psi sub t times psi sub e, and look at the product of these two values. If it happens to be more than 1.7, just use 1.7. This is going to be like a cap value. So for example, someone says, I'm going to have top rebars. At the same time, also I have epoxy coating of 1.5, right? I have this case. I said, okay, if psi sub t is going to be 1.3, if psi sub e is going to be 1.5. What value should I use for this two product, for the product of these two values? Any idea?
1.7.
Exactly correct. Thank you. Meaning once the product of these two values to go above 1.7, just use 1.7. This is correct, Eddie. Thank you. How about the size? We talked about the size for the size of the rebar. It says use 0.8, which means that you're going to need here less development length. When the bar size is going to be number 6 and smaller. For number 7 and larger, you're going to be using 1.0. Now it makes sense. Now I understand the meaning of this size. Because when you have a smaller size for the same cross-section area, you're going to have more surface area, more bond. This is why the length is going to be smaller. Other item, lambda factor that we talked about, which is a 0.75 for the lightweight aggregate, for lightweight concrete. C sub B, we discussed it. So I said that I have 5 factors. What are the 5 factors? 3 size, 1 CB, and KTR. Now we cover the 3 size and the CB. We say here's the CB, and here's the size. Now how about KTR? It says it depends on the amount of transverse reinforcement. For example, in a case like this, you have ties. When you have more ties, what do you think? What's going to happen? When you have more bond or less bond? Versus no ties at all. So someone's going to say here, having some rebars in any direction is going to help out. So when you put ties here in the other direction, right? In this direction, your transverse direction to the bar that you're trying to develop or splice, it's going to give you more bond. So in this case, adding more ties would reduce L sub D. This is why we have this factor KTR. When you have this KTR is going to go larger, what's going to happen? The entire number here is going to get smaller. And then it says here, just use it equal to 0. But you have an equation for it. It depends on the amount of transverse reinforcement, about the number of bars, and the whole thing. So for us, for this course, and also whenever that you're doing a design, just take this KTR is going to be equal to 0. When you use this equation, also you have another cap. Look at this. It says when you take the CB plus the KTR, which is now become 0, I'm going to say now this becomes 0. It needs to be less than 2.5. So if this CB divided by DB turns to be, let's say 4 or 5, just use 2.5 in this equation. That's it. It's going to be like a cap value. We have this table in the code, and this table to help you out to find out the value, which is K sub D, 3 divided by 40, F sub Y divided by square root of F prime C. And actually this factor or this table here, you can just ignore it because look at this. What's K sub D? Just look at this again here, 3 divided by 40, Fy divided by F prime C. I'm going to be looking at this. I'm going to say, this is exactly this thing here, right? Not including this lambda factor for the lightweight concrete, right? So I don't really need this table, but if you like to use it, go ahead and use it. I would just take this to be 60 psi and F prime C, just use the value as in PSI. But if you like to use this table, this is fine. This K sub D, which is the product of this few factors, is going to be equal to any one of these values for different f sub y's and different f prime c. Question is, when it comes to 500, what do you do? I'm going to say just use this equation. It's not a tough equation. Just use the equation. In your second midterm, in your final, this equation is going to be given to you. So you just use the equation. Don't try to use the table though. It's not really saving that much time. There's another factor here that says you can reduce the length of this development length. L sub D, you can reduce it. It depends on the amount of rebars that you put in there. So let's say your section here needs 3 number 5. In reality, you provided 4 number 5. So the amount of tension in the rebars it's not going to be whatever that you plan to have it. For example, when you have here 4 number 5, and then you take 0.31 times 60 KSI for each one of this rebar, you're going to have big tension area. Compared to what is needed, you need only 3 rebars. So you say you can reduce the development length by a factor, which is this reduction factor K sub ER. It depends how much was required by how much is provided. Let's say I was looking for this AS to be 3 number 5. I provided 4. It means I can use 3/4 of this development length. Make sense? Yes? No?
Yes.
Okay, thank you. Now let's see here step by step. How would you do this? You can do the KD from table 1, which is this table. You can just solve this equation. Number 2, you have the psi values based on the given information, the problem. And then you do the check, psi sub E times psi sub T to be within 1.7 as a cap value. You figure out C sub B, the smallest edge distance, center of the rebar to the edge. KTR, usually we take it as 0. So I'm going to put it here. Just take it here to be 0. No worries about it. And then you do the check for also this cap value, CB plus KTR divided by DB to be within 2.5. And then if you really want to apply this KER, use it. If I didn't ask you for it, no information is provided about what is needed, what is provided. Don't worry about it. And then after that, you do L sub D. One last thing here that you need to know, L sub D minimum is going to be 12 inches. So if your analysis showed, for example, 10 inches, just use 12. This is also based on the code. So it's going to be like a step-by-step. 7. We have one good example. It's about development length. And it says here, calculate the tensile development length required for number 8 rebar. Which number 8? I'm going to say this is going to be the number 8 rebar that we're interested in. More than 12 inches of fresh concrete to be cast below the rebar. You see this more than 12 inches? What does mean by that? What's the conclusion? Top rebars. How do I know that? Because it says if this is going to be more than 12 inches, you consider it to be top rebars. You're going to have specific psi sub T for it. It says here lightweight concrete. So when it says here lightweight concrete, what's the conclusion? I'm going to say lambda equals 0.75. F sub y is 60,000, F prime C 4,000. The tie is going to be number 4, uncoated. What does it mean by uncoated? Psi. Which psi? E equals 1.0. So okay, let me solve the problem and see how much is the development length. This KD is going to be 71.2. This is going to be the product that I was just talking about. Look at this. 60 and 4,000 is going to be 71.2. Or you can just use the equation. Okay, good. Simple. I have top rebars because you have more than 12 inches. So psi sub t is going to be 1.3. For the uncoated bars, conventional rebars, no epoxy is going to be 1.0. For the rebar size, it's going to be number 8, so psi sub s is going to be 1. If this is going to be number 6 or smaller, it's going to be 0.8. Lambda for lightweight aggregate or concrete is going to be 0.75. The product of psi sub t times psi sub e, just try this, is going to be 1.3. So just use the value as is. There is no reduction needed here because we're still below the cap. C sub b, I have here 2 values. Let me here skip this and go to next slide. Here is the same slide that we discussed earlier. I'm going to have for this rebar here C sub b1, C sub b2. I'm going to be taking it to be 2 inches. So we looked at this already before. So let me go back here to the previous slide. I'm going to say C sub b is going to be 2 inches. KTR, I'm going to take it to 0. Now let me try here this product or this value, this term. C sub b is going to be 2. KTR is how much? How much did we say for KTR? We're going to say here 0. Divide by dB, the bar diameter, less than 2.5. We are fine. I'm going to say here, let me try my equation. It's going to be 71.2 for this factor. Divide by 0.75. And then you have here 1.3 for the top rebars. Epoxy, no epoxy coating. The size, it's number 8, more than number 7. It's going to be 1. C sub b, divided by dB is going to be 2. Times 1, the bar diameter is going to be 1. I'm getting here 61.7 inches, 12 inches. I'm going to be using 62 inches. So, okay, good. Now I know how to figure out this length, development length needed. So, okay, let me look at another example. Calculate development length required for number 9 rebars in the top of 15-inch thick reinforced concrete slab. Now, where is this rebar? It says number 9. Here it is, number 9 rebars, meaning this rebar. We are trying to find out L sub D. Here's L sub D. If this is here 15-inch, I want you to look quickly and tell me if this is going to be top rebar or bottom rebar. Should I consider this to be top rebars? Is this distance from here to there, right? Is this more than 12 inches? 12 inches or more? Can someone help quick?
Yes, since the clear distance is only 3¼ inches or 3/4 of an inch.
Good, all right. So in this case, I'm gonna have more than 12 inches. It's gonna be top rebar. I have a question here. The question is, do we really need to use here K sub ER, the reduction factor? I'm gonna say for this problem here. Well, in this problem here, no one mentioned anything on what was needed originally. So I'm gonna say, if no one asked the question or gave me what is already needed, in this case, I don't really need to mention K sub ER. Just use it as is. I mean, use LD as is. Don't reduce it. Now to continue with this problem here, it says the bars are epoxy coated, meaning now I need to figure out the spacing is going to be an issue, and the cover also is going to be an issue. If I go back here and take you back to the slide where it has this epoxy coated factor, it says here for the epoxy coated, when the cover is going to be less than 3 dB, I have number 9 and the cover is 3/4 inch. What do you think? Do you think I'm going to be within this category, 1.5 or 1.2 or what? The rebar size I have is number 9, more than an inch, and the cover is 3/4 inch. What psi sub e should I use? 1.5 or 1.2? Of course, 1.5, because the cover is very small. It's going to be 1.5 because the cover is very small. The cover is less than 3 dB. Therefore, I'm going to be within this category. So, okay. Let me look here for this psi sub E. So psi sub E, as we say, is going to be 1.5, and here's the reason. Top rebar is going to be 1.3. K sub D, I have it, which is the concrete strength and yield strength of the steel. Normal weight concrete is going to be 1. They didn't say lightweight concrete. If no one said lightweight concrete, it means it's going to be normal weight concrete. Try this product to keep it with a 1.7. It's going to be 195. I'm going to be using 1.7. Try the C sub B1 and 2. I guess you guys know how to do here C sub B1 and 2. Look from the center of the rebar to the top, and from the center of the rebar to 1/2 the way between these two rebars, like this distance here. Right? It's going to be CB1 and CB2. We tried this CB1 and CB2, and based on the top cover, it's going to be 1.3. This is a value that I need to use in my analysis. Now I need to do the other check, which is this. CB plus KTR, which is a 0, divided by DB. Smaller than 2.5. So I said, well, let me use this equation. Look at here, psi sub T multiplied by psi sub E. I know it's going to be 195, but here's the value I'm going to be using in my analysis, 1.7. Great. At the end, development length here becomes 1117.2. I need to do this last check versus 12 inches. At the end, I use 118 inches. Any questions?
No questions here. All good.
Okay, great. All right, we're done for today. Please go ahead and sign out. And if you have any questions, let's meet at the office hour. Thank you.